Now let's talk about a bit early, 9 o'clock in the morning. Let's talk about beer. Imagine a brewery with an average wastewater flow of, let's say, over 4,000 cubic meter a day, and then with an average COD concentration of 4 kilograms per cube. The products are the nice beers that you see here, but the question to you all is, how much money would the brewery save on electricity costs, so kilowatt hours, if the company applies anaerobic high rate wastewater treatment instead of activated sludge? The question is not that strange, because if you go worldwide, there are quite some beer brewers having activated sludge, while others having anaerobic high rate treatment. Do they save 200,000 per year on euros? Do they save 700,000 euro per year? Do they save over a million, 1.2 million euros per year? Maybe up to 2.2 million euros per year? So guess what's the answer? A, B, C, or D? Okay, I don't have to know it. We will see it a little bit later. But keep it in mind. Well, to make this balance, to make this calculation, let's go first one slide to the basics. And this slide. If we have an anaerobic conversion process, we start off with the biochemical energy expressed as COD coming in, and it has a removal efficiency of, let's say, 80%, 85%. Then the remainders of the COD in the effluent. Now, one of the biggest tricks is that most of the energy, the COD, is entailed in the end product. The COD is not destructed like an activated sludge, where oxygen is the terminal electron acceptor, but it is contained in the end product. That part of the carbon gets completely oxidized to CO2, and the other part of the carbon gets completely reduced to CH4, where all the COD is. And also interesting, there's hardly any sludge production, so there's no wastage. Now, if we express this in a megajoule, we have energy savings applying AD instead of activated sludge. We can calculate that 1 kilograms of COD contains a biochemical energy content of 12.4 megajoules per kilogram. Now, we don't have to save, so we save 0.5 to 1 kilowatt hour per kilogram, or 1.8 to 3.6 megajoule. Now, if you extract that energy from a fossil fuel plant, then of course we have to divide it by 1/3, because there's only 1/3 of efficiency in such power plants. So the maximum energy gainings, if you look to the overall energy gainings, is up to 20 megajoule per kilogram COD removed. Not all of that is for the benefit of the company, of course. But let's focus on this company. The same, here is the brewer. And here are the flows, and here is the concentration of COD. And this brewer discharges about 17 tons COD per day. 1 ton of COD is equal more or less 12.4 gigajoule on the lower heat value. It's about 3.4 megawatt hour. Now, this 17 tons is treated with an efficiency of 85%, so up to 50 megawatt hour per day can be used if you turn it directly in thermal heat, if you have a 100% efficiency conversion to heat, which is not the case, of course. If you turn this into electricity, now let's calculate with 40% of combined heat power efficiency, then it's about 20 megawatt hour electric per day that can be generated by that energy. Now, there's no saving, so up to 1 kilowatt hour electric per kilogram COD can be saved, 0.5 to 1 kilowatt hour. And then you gain another almost 15 megawatt hour electric per day. Now, if you all sum this up, then with the current energy price for industries, which is 0.175 euro per kilowatt hour, so 17.5 euro cents per kilowatt hour, then we come to answer D. So it's 2.2 million euros per year sold on electricity. Now, if you then would add also the benefits on sludge, because you don't produce any sludge, and sludge treatment in the Netherlands is incineration at quite a high cost, maybe 400 euros per ton on gate fee, depending where you are in the Netherlands. Then, and meanwhile, the anaerobic excess sludge brings in money, even 200 euros per cube or something. So that will also add to the benefits. So there are quite some benefits. And another benefit is CO2 emission reduction. This is the amount of ton of CO2 that electricity plant in the Netherlands on the average produces emits 0.65 ton per megawatt hour electric. And the electricity from the biogas that is equal to about 13 tons CO2 emission reduction. And no electricity for aeration is another 10 tons CO2 emission reduction. So in total, over 20 tons CO2 emission reduction per day. Now, tradable is of course the green energy from the methane, and that is equal to 1,280 euros per day, or €500,000 per year. Now, all this in the past 40 years was developed under the umbrella of anaerobic high rate treatment, and a number of industries are applying this, particularly in these strongly polluted, organically polluted wastewaters. They are implemented. They have wastewater treatment, but not in the world. In the world, you see a lot of organically polluted streams that are still using activated sludge. Now, the Netherlands was a front runner, and my predecessor at Wageningen University, Professor Lettig, developed the technology. Dutch companies took up the technology, and a myriad of anaerobic reactor systems were developed. And I name here particularly two companies, the Biothink company, Parks company, developing all kinds of reactors, of which I don't have any time now to explain on anything. But if you are interested, then please copy this QR, and you find a professional education course in the web where this is explained to further details. At the TU Delft, in the past 10-20 years, we were focusing on the development of membrane bioreactors. And the reason for that is, well, simplification of the treatment train, because you can put everything in the reactor, no pre-treatment, no post-treatment of the anaerobic reactor, slurry, solids, so high concentration of solids, fats, everything can be dumped into the anaerobic reactor, and you have a membrane barrier. Now, what we found, particularly with the first simple submerged membrane bioreactors, that despite expectation, we got low critical fluxes. Depending on the wastewater composition, the more complex the substrates are, the lower the critical fluxes are. And in fact, if you have a critical flux of 5 to 10, not very attractive for commercial applications. But the good thing is that there's so much sludge in the anaerobic reactor that if you start filtering, the cake layer that is deposited on the membrane is blocking the pores. It's not blocking the pores, it's protecting the pores for blockage. And what we observed is very little membrane permeability loss, and the entire resistance of the membrane could be attributed to the cake resistance. So we developed automated routines where we dosed coagulants or flocculants to bind the sludge and to increase the sludge filterability. So with this system, you do have bioenergy recovery, but you also have water recovery, because most of the membranes are now equipped with ultrafiltration membranes. Now, the breakthrough of anaerobic MBRs came with side stream configurations, where you don't work on the critical flux according to its weak definition, but to the sustainable flux. And it means that you apply quite a high shear force to clean the membrane, high upflow velocities, 1-2 meters per second, and in that sense you can go to 15-25 LMH, and that means a commercial flux, commercial of interest. But I have to say that now the bioenergy that you can withdraw from the anaerobic reactor, most of that bioenergy is simply used to turn it into electricity for operating the plant. So that covers mostly the energy cost for membrane operation. But nonetheless, if you're interested in high quality water, then the external membranes, they ease the operation, of course, but it brings also the anaerobic membrane to a high TRL level. Now, at this moment, we are assessing the potentials for chemical wastewater, and that is a very difficult market, because chemical companies, they don't like biology. They like to evaporate and incinerate. But nonetheless, if you look to the biology itself, an anaerobic membrane is quite of interest, because you have an absolute barrier, the membrane, and bacteria on these substrates, they don't grow fast. So you would like to retain all the bacteria that you grow inside the anaerobic reactor. So with an anaerobic MBR for chemical wastewaters, you do have in situ bio-augmentation of these specialized bacteria that you need. And these long solids retention times, because you can decide on yourself what is a solids retention time, you enhance the specific catabolic conversion capacities, for instance, of these aromatic compounds that you see here in the graph, the phenols, the catechol, the resveratrol, etc. And the effluent is solids free. And that means that is quite interesting for effluent recovery as processed water and water. That is an issue also in the chemical industry. Now, some success stories came also from Biothane. They have over 25 references now, and this is an example plant for chocolate and pet food in Poland, where you see the flux nicely stabilizing up to 25 LMH. You see also the COD removal, quite high concentrations of COD, 15,000 up to 20,000 in the influent, and about 0 in the effluent. So these type of systems, they have a removal efficiency of 98% in COD and almost completely on suspended solids. Now that gave the idea of the Biothane company, together with the mother company of Veolia. Why don't we combine that? An anaerobic MBR, we have a perfect pre-treatment with the UF skid, and we coupled it to an RO. Now the water is anaerobic when it goes to the RO, and that means you also have way less fouling of the spiral wound RO membranes if you keep it anaerobic, because under anaerobic conditions bacteria hardly grow, and that means that the number of cleaning in place to operate these membranes are way less than when you first aerate it and then go to the RO. Now they have quite an interesting example in South Africa in a dairy where the license to operate of this company was given under the conditions that they reclaim all their wastewater as processed water, as water extraction in that vulnerable area was not in fact allowed. Now already running quite some time, well, I would like to address some words to the conventional municipal sewage, because also there we see a clear link between wastewater and energy. Now this is a system that we have from the past, from the last century, but it's a common system that is nowadays applied worldwide, and most of the treatment plants in the Netherlands are also based on either UCT or carousels. In this, the sludge digester plays an important role because it stabilizes the excess sludge to get some energy out of it, but also to reduce the volume, to reduce the sludge incineration cost, and to recover the bioenergy, the biogas, to be used as an energy source inside the treatment plant. And moreover, if you digest small particles, if the digester works fine, then you also improve the dewatering characteristics. Now, if you couple this to the Green Deal, then if you look closely to AD, this touches perfectly with the current European Green Deal that was adopted last year. Because in fact, this anaerobic digester is a kind of a core technology for generating quite some resources from wastewaters and waste streams like sludges. And if you look closely to the municipal sector, then in fact all these black arrows means association with sludge. So this sludge digester plays a very crucial role in advancing to comply with the European Green Deal's goals. Now, then the question of many water authorities in the Netherlands, can we achieve energy neutrality? Now, some of the wastewater treatment plants, well, they claim they have now energy neutrality, but of course there's a lot of import of sludges from small wastewater treatment plants to the central sludge digester for generating the energy. So it's not completely energy neutral, but a lot of research has been done to improve the digestive systems, for instance, to enhance the mixing and to pre-treat the sludge with thermal hydrolysis processes that can be the cystic lysozymes, or to do co-digestions with green wastes, external green wastes, or sludges from small treatment plants, and maybe to go to higher energy conversion efficiency technology like solid oxide fuel cells, which is still in the TRL level of 6-7, not in commercial scale. I would like to mention one development in which we cooperated with Royal Haskoning, and that was a development of cascade reactors, which was quite interesting, and that followed also some from research that we did from our side at TU Delft, and insights that were gained at the Royal Haskoning group. Anyway, this teamwork resulted in a quite interesting cascade system, and in this cascade systems that can be implemented quite easily with existing digesters, in which you, for instance, here is a wastewater treatment with one digester that was then partitioned in 3 cascade reactors, and that was then complemented with a 4th backup reactor, a methanogenic reactor. And because of the high loading in the first 3 reactors, you produce a lot of more hydrolytic capacity to convert the sludges. And yeah, at this moment, this technology is baptized as EFIRA. If I'm informed correctly, then in 2025, at this moment, we have 16 references already. Meanwhile, the research was done very, very recently, in the past 10 years, let's so to say. And the SRT of this entire digestion system is only 7 to 8 days, so that is quite interesting low. Now, to close off, a few words about one of the striking pollutants that we have in the Netherlands, and that is ammonium. Because ammonium is like water, very small, they look alike, but what to do with it? Now, in the past, we send everything back. If you have a digester, you have dewatering, you have reject water, you send it up front to the wastewater treatment plant. But then you get nitrification, denitrification, at the expense of BOD, at the expense of energy. However, in the past 10 years, we developed a technology to extract this ammonium using electrodialysis combined with bipolar membrane electrodialysis. And it looks like this. We have first, we had a simulated reject water, which is, we thought, ammonium bicarbonate, and one side an anode, another side a cathode, and the anions go to the anode, the cations to the cathode. And with a bipolar membrane, you are not splitting the water, but you are ionizing the water in a hydroxyl group and a proton. And the hydroxyl group merges with the ammonium, and the proton merges with the bicarbonate. And that is interesting because then you make ammonium hydroxide or ammonium water, which can be extracted, and the pH goes up because of the hydroxyl group, so it can be extracted as a gas. In fact, ammonium removal at low energy costs, production of gaseous ammonium, you don't need to add alkaline because you produce the alkaline in this bipolar membrane cell, and you have a production of CO2 in the other cell. Now, what does it cost in energy? If you only up concentrate it with the ammonium, then it costs you about 5 megajoule per kilogram nitrogen. And if you would like to separate it, so ammonium hydroxide and bicarbonate CO2, it costs you about 20 megajoule per kilogram N. Now, the intrinsic energy, biochemical energy content of ammonium is 21 megajoule per kilogram N, and Haber-Bosch to produce ammonium is about, now with methane gas, it costs you about 30 megajoule per kilogram N. And if you do that with electrolysis, it costs you 100 megajoule per kilogram N. So this is quite interesting that you can recover ammonium in this way, either as a resource or as an energy source. Because this ammonium, it can be used to fuel a solid oxide fuel cell where you have an internal reforming of ammonium to nitrogen gas and the hydrogen goes to the anode and delivers the electricity. Now, the technology is patented, and based on this technology, we went to, this is the final slide, we went to some occasions to treat real reject water. And then the picture changes, because real reject water, and I guess that the people in the audience, they know as quite well, that's a mess, because you have a lot of competing ions, you have disturbing anions, non-controlled precipitation, membrane fouling, membrane lifetime, and this is completely different approach than when you treat ammonium bicarbonate as assimilated solutions. Now, we came up with 2 options. The first option is now currently conducted by our PhD, Yusuf Kandiakos. He is combining an ED reversal for up-concentrating ammonium. And inside this electrodialysis cell, he uses monovalent selective cation exchange membrane, so no bivalent cations that passes, well, not completely, but they are selectively retained, so you reduce the precipitation. And then he made a bipolar membrane electrodialysis stack with only 2 chambers, and that means he has only 1 alkaline, and then we have an acid step, and this acid step is combined with the electrodialysis. And with this acid step, you reduce the pH, preventing precipitation of the bivalent cations that passes still the monovalent cation exchange membrane. Now, then you optimize the energy by operating with the pulse pause operation, and that pattern is currently pending. But still, you have then to deal with this very difficult matrix. And the other option is to change the matrix, and that is what we do with the company NIAS at this moment. We have two PhDs working on that. And then we have a conventional air stripping acid scrubbing, and the acid, which conventionally is sulfuric acid. And the acid then is used in the scrubber to bind ammonium, and you make ammonium sulfate, which was seen as an interesting compound for fertilization, but it is now clear ammonium sulfate has not really a high value. In fact, the sulfuric acid is more expensive, ammonium sulfate. So that commercially, particularly here in the Netherlands, Flanders, where we have a lot of ammonium, is not a real good solution. So with the bipolar membrane electrolyte dialysis setup, we can extract in a similar way on one side ammonium hydroxide, and at the other side the acid. We can recover the acid and then reuse the acid in the scrubber again. That is quite interesting. Now, in our last research, what we focus on is to kick out the sulfuric acid and bring in organic acids. Organic acids, citric acids, are way more expensive, but you don't lose them. You simply keep on recycling them between the BPMAD and the scrubber. And that means with an organic acid, so the pH values are higher. They don't have to go to pH 2. So you don't have competing ions with ammonium. You have a way more higher efficiency in transferring ammonium to the alkaline cell than when you work with a low pH sulfuric acid. So less energy, and you gain more ammonium as a resource or as an energy, as a fuel, as an energy containing end product. Take home message from here: wastewater is really full of energy. Recovery and reuse adds to real sustainability. And anaerobic digestion is still, in my point of view, the workhorse of treating organic streams. And ammonium is an energy carrier and a resource. Recover it instead of destruct it. Thanks for your attention.
Thank you very much, Professor Van Lier, for this overview as an introduction for the rest of this webinar. So the technology is kind of old already, and then some companies took it into production, and now they have their track record. Some questions are coming in. That's excellent. We can deal with them. Jules, just for my understanding,